Welcome to lecture series on design and analysis of algorithm. In today's lecture series, we are going to see a topic under dynamic programming, which is optimal binary search tree. So before we move on to the topic, let's have a quick recall on the topics we have seen earlier. We have seen the algorithmic problem solving approach, and we have also seen the important problem types, what a brute force approach is, what are the types of problem that can be solved using brute force approach, and what does divide and conquer technique, and the problems that can be solved using divide and conquer technique. So today we are going to discuss about how to build a dictionary online with fast lookup, and we will also see about the OBST approach, which is used for dictionary application, and how OBST can be constructed using dynamic programming approach and its application. So now this is how a dictionary will look like, right? If you want to search for a word in this dictionary, do you think it is an easier process if the words are randomly located? The answer is absolutely no, right? So here it is a dictionary. You are going to search for an English word. Uh, so in such a way that you want to find its meaning quickly. That is why you build a dictionary. So when you build a dictionary with a normal binary search tree, a balanced binary search tree would have a time complexity of order of log n, and its total cost is around 20 lakhs. For example, if you want to search for a word apple, the total number of search that happened is around 10 lakh and depth of the node would be 2. So its cost is obviously 20 lakhs. So if you restructure the binary search tree by making the word apple, because this is having the highest search cost. So when this node is made as the root node, the optimal binary search tree will look like this. So apple will become the root node and other nodes will follow the node apple. So this is the approach which is normally followed. You will build a binary balanced binary search. You will collect the search information. You will calculate the probabilistic search. You will calculate an optimal binary search tree. Then you will change the current binary search tree to an optimal binary search tree. So assume you are given some of the keys and its probabilities. Probability represents the occurrence, probability of occurrence. So you are given a sequence of keys k equal to k1, k2, k3 to kn. So in such a way that each of the key is distinct and probability of the key is also given. So uh, the total here pi plus qi is the total probability of the key will be equal to 1. Example, here you are given the words and its total search and probability will also be mentioned. So when we search for a word ki, its search time is equal to the node depth of ki. When we search for a word in the range of the depth, search time is equal to the node depth of dj. So expected search time will be the summation of probability of I into node depth of ki plus summation of qi into node depth of ki. So you are given set of probabilities P and Q. So you need to construct a binary search tree whose expected search time is minimized. So such binary search tree is called as optimal binary search tree. So here is a dynamic programming approach which is used to solve this particular problem. It solves the problem by combining the solution to the sub-problems. That is how a dynamic programming approach works, which we have seen in the earlier lecture videos. It uses memorization as well as tabulation technique. So the first step is, this is how the structure of OBST looks like. If it is an OBST, it has a subtree T, then the subtree should also be an optimal binary search tree. Any subtree in an optimal binary search tree is again an OBST. You have to decide the root of OBST, which is the major process. In order to find the OBST, you have to decide its root and root of each subtree as well. Here, E of edge of I, comma j is represented as the expected time searching for the OBST that contains the keys ki to kn. So, weight of I, comma j is the sum of probabilities of the key. Next, you have to try all the roots to find the minimum searching time. So for any of j which is greater than or equal to I, you have to find e of I, comma j, which is minimum of the values. And we use bottom-up approach here. So here the value of e of I, comma j is stored in a root 2D table. And the weight of the 2D table is stored in W of I comma j. We also use a table called as root of I comma j root table for recording the root of the subtrees containing the keys. So here the time complexity is measured to be order of n power 3. So you need to optimize the solution, right? We optimize the solution like the root of the tree is chosen so that most closely balance the total weight of left and right subtree. So some of its applications include Huffman tree and optimal routing lookup. Here are some of the assessment questions for your practice. So what approach is being followed in OBST? Dynamic programming approach is followed in OBST, which is not an application of OBST. Obviously, it is uh, yes, a single source shortest path, which is not an application of OBST. So this is a mind map of topics we have seen so far. Hope you understood the logic behind optimal binary search tree, and here are some of the references. So in the next lecture video, we will discuss some other problem solving approach. Thanks for watching.